We're now in the process of going live, but we should wait until 10:02. We're live.
So welcome everyone to section 9 of CSL 21. We're going to have 4 talks in this session, and we are going to start with Pham, and he's going to talk about typable fragments of polynomial automatic amortized resource analysis.
Hello, my name is Pham of Carnegie Mellon University, and today I will present typable fragments of polynomial automatic amortized resource analysis. This is joint work with Jan Hoffmann. ARA, which stands for Automatic Amortized Resource Analysis, is a type-based technique for resource analysis of programs. Given a program, ARA infers a resource annotated type which encapsulates worst-case bounds of computational costs. In the context of ARA, computational cost can be anything, including time, memory, and power. However, in this presentation and paper, we focus on the running time. For any type system, we can ask 2 questions. The first is how can we semantically characterize typable programs? For example, in the simply typed lambda calculus, its typable fragment is known to precisely correspond to the set of extended polynomials. The second question is, what is an easy to understand if sufficient condition for typability? For example, type inference of system F is undecidable, but there is an easy to understand sufficient condition for typability in system F, namely the Hindley-Milner type system. In this paper, we ask the same 2 questions for ARA. To provide semantic characterization of ARA, we show that for any polynomial time Turing machine, it can be converted to a program typable in ARA. In this translation, the input-output relations remain identical. In addition, the polynomial cost bound of the new program is larger than or equal to the running time of the Turing machine. In other words, the polynomial cost bound of the new program is a valid bound on the running time of the Turing machine. For the second question, we propose a simple sufficient condition called inherently polynomial time. We also prove that it implies typability of ARA under some extra restrictions. We have 2 criteria for a candidate sufficient condition. Firstly, we don't want the sufficient condition to be identical to the type system of ARA. The sufficient condition will likely be defined axiomatically, and the type system of ARA is also defined axiomatically. So it would not be interesting if the sufficient condition is identical to the type system of ARA. Secondly, we would like the sufficient condition to be easy to understand. To analyze programs using ARA, because programs are sometimes untypable, users of ARA need to tweak their programs. This will require deep understanding of the underlying type system. To reduce the burden of non-expert users of ARA, we want the sufficient condition to be easy to understand so that users will have an intuitive understanding of when programs will be typable in ARA. Now that I have talked about the motivation, I will next explain the basics of ARA. After that, I will describe the sufficient condition of ARA. This presentation will not delve into our first contribution on the semantic characterization of ARA. Its details are available in the paper. The key idea behind ARA is a potential method for amortized analysis. To give a high-level overview, consider a program expressed as a transition system. On the slide, each S is a program state. To each s, we assign a non-negative number phi, which is called potential. Suppose that we assign these phi's in such a way that for each phi, it is larger than or equal to the next phi plus the cost for the state transition. If this condition holds for each phi, then we can conclude that the initial phi, namely phi 0, is a worst-case upper bound on the total cost. To illustrate ARA with a concrete example, consider a function double which doubles the input list. For instance, given a list containing A, B, C, and D, the double function returns a list containing 2 A's followed by 2 B's, 2 C's, and 2 D's. For the running time, suppose that it costs 1 unit of potential to process one element in the list. Additionally, suppose that we give a total of 4 units of potential to the input list, and these units are distributed evenly across all 4 elements, as shown on the slide. If the double function is implemented using recursion, the last element will be processed first. So the potential in the last element is consumed, and we duplicate this element. Next, to process the next element, we consume its potential and duplicate it. This process continues, and the final output is a list storing 0 potential in each element. Therefore, we can type the double function as capital L with a superscript 1, arrow L with a superscript 0. These superscripts denote how much potential we store in each list element. This is not the only possible resource annotated type of the double function. For example, if we assign 3 units of potential to each element, then for each element we consume 1 unit of potential and split the remaining 2 units between the old and new list elements. As a result, another possible resource annotated type is L of 3 goes to L of 1. ARA offers several benefits. Firstly, the type inference of ARA, which is based on linear program solving, is fully automated. Secondly, because ARA is based on amortized analysis, its analysis is more precise than naive summation of all costs. Thirdly, ARA is sound. That is, if a program is typable in ARA, its resource annotated type is a valid cost bound. Furthermore, the soundness has been formally proved, unlike some other resource analysis techniques whose soundness is only proved informally. Lastly, we can use type derivations of ARA as certificates of cost bounds because these derivations are easy to check. The example of ARA on the previous slide only uses linear potential. Specifically, we know that the cost bound of the double function is the size of x. However, in general, ARA is capable of inferring multivariate polynomial bounds. For instance, for the multiply function, which returns a list of size x times size y, ARA can infer that its cost bound is indeed the size of x times the size of y. Thus, the cost bounds derived by ARA are multivariate polynomials. Next, I will walk through the high-level design of the sufficient condition we propose, which we call inherently polynomial time. Firstly, any typable program in ARA must run in polynomial time. This is because ARA is sound in the sense that whenever ARA returns a cost bound, the bound is valid. Therefore, to design a sufficient condition, we require that primitive recursion is used instead of general recursion, so that termination is guaranteed. Additionally, the program must run in polynomial time. The next step is to observe that ARA is a type system and therefore is computational. This means giving a program to type it in ARA, every subexpression of the program must be typable as well. This suggests that whatever sufficient condition we propose, it should apply to not only the whole expression, but also every subexpression. Therefore, since we know from the first design step that the entire expression must be polynomial time, every subexpression must be polynomial time too. Finally, for the last design decision, consider a primitive recursion of this form. Here we have two branches, and in the second branch, we pattern match x against y cons ys. Z denotes the recursive result, and E1, which is called the stepping function, describes how we process y, ys, and z to construct the output. From the previous step in the design of the sufficient condition, we know that every subexpression must be polynomial time. So suppose that E0 and E1 are both polynomial time. Does it automatically imply that E, which is the entire primitive recursion, is also polynomial time? The answer is no. To illustrate the problem, consider this example where the stepping function doubles Z. This means in each recursive step, we double the recursive result. Hence, in the worst case, the running time is exponential, which is beyond the capability of ARA. The root of the trouble is that the running time of the stepping function, which appends z to itself, runs in linear time in the size of z. Therefore, to preclude this example, we require that the stepping function's running time is constant in the size of z. In summary, we propose a sufficient condition consisting of three requirements. First, we use primitive recursion. Second, the sufficient condition is compositional, hence every subexpression must be polynomial time. Third, the running time of the stepping function must be constant in the size of z. Now, in the last part of this presentation, I described the challenges we faced in proving that inherently polynomial time implies typability of ARA. This is a theorem that we want to prove ultimately. Given a program E, if E is inherently polynomial time, then there exist P and Q such that E can be typed using P and Q. Here, P is input potential, that is, the potential we supply to E before it is evaluated. Q is output potential, that is, the leftover potential after E is evaluated. However, this naive statement of the theorem is not compositional. And as a consequence, we have a problem with a let binding. Consider the let binding let x equal E1 in E2. Suppose that in order to type E2, we need to have one battery's worth of potential in X. Furthermore, suppose that in order to have one battery remaining in X after E1 is evaluated, we need two batteries worth of potential at the beginning. Therefore, in order to prove typability of the whole let binding, the leftover potential in X cannot be arbitrary. It must be at least one battery. However, at present, the theorem doesn't let us specify the output potential Q. The theorem only states that some Q exists. Therefore, we need a stronger theorem where Q is universally quantified, and for each Q, there exists some suitable input potential P. To describe the next challenge, consider a primitive recursion of this form, where Z is a recursive result and E1 is the stepping function. The way primitive recursion works is that we start with E0, which is the output in case X is the empty list. We then apply the stepping function E1 to E0 to obtain Z1, which is the second recursive result. We repeat this process to obtain Z2, Z3, and so on. Note that all of E0 and Z's must have the same type. It is because the type of the primitive recursion should be valid regardless of the length of input list X. Therefore, in a sense, the type of primitive recursion is a loop invariant. To prove that inherently polynomial time implies typability of ARA, we need to show that primitive recursion is always typable. In other words, we need to show that a loop invariant always exists under the assumption of inherently polynomial time. Now let us look at the stepping function E1 of primitive recursion. It is not enough to just find some resource annotated type of E1. We must additionally require Z, which is a recursive result, and E1 to have the same resource annotation. This is why on the slide, both Z and E1 are given yellow batteries. By the way, by the definition of inherently polynomial time, we know that E1 must run in constant time in the size of Z. That is, conceptually, E1 should not use any potential stored inside Z. This is why it is reasonable to expect that Z and E1 can have the same resource annotation. This typing of a stepping function in primitive recursion is just a special case. To generalize this, consider a term E whose free variables are X's and V's. Suppose that the running time of E is constant in the size of each Vi. Then we would like to prove that E is typable in such a way that its resource annotation is the same as the resource annotation of each Vi. This is why on the slide, all of V's and E are given batteries of the same color. In this case, the input potential of E is said to be a uniform resource annotation of yellow with respect to V1 up to Vn. In this way, we introduce the notion of uniform resource annotations, and generalizing this notion to multivariate polynomial ARA was a major challenge. In summary, our contributions are the following. We first semantically characterized the typable fragment of ARA by embedding polynomial time Turing machines in ARA. Next, we proposed a sufficient condition for typability in ARA, which we call inherently polynomial time. Finally, we proved that inherently polynomial time implies typability of ARA under two restrictions, on variable sharing and nested lists. Unfortunately, we did not manage to prove the full theorem without any restrictions, and we leave it to future work. Thank you so much for your attention.
Thank you very much, Long. Is there any questions? I mean, you can ask questions either by raising your hand or writing in the chat your name and the question. In the meanwhile, I have a couple of questions. So you said at the end that you had a problem with nesting, right? I mean the full typability theorem is a problem because of nesting, right? So
yes.
since the paper was published and now, did you have any other new insight or something that you think might work, or have you thought about this a little bit more?
So we know, but I feel like that problem is, so I speculate that we just need to modify the inductive hypothesis of the theorem a bit to accommodate, to overcome that restriction. But ideally, we also want to overcome the first restriction, which is the one on variable sharing. And we found it fairly challenging to overcome it, which is why it is still unsolved.
I see.
Yeah.
Okay, great. I have another question. So
yeah.
can you say something about related work? I mean, what people are doing in this area as well.
Oh, I see. Right. So regarding the big picture, I mean, so in ARA, there are several directions. There are several lines of research in this big area of ARA. Well, let's see. So originally, ARA is a resource analysis for multivariate polynomial bounds. So, for example, people have extended it to exponential bounds, for example, or people have applied ARA to probabilistic programming or concurrent programming, for example. But if we consider sort of the mix of ARA and the kind of research we did in this paper, namely, finding a nice and easy to understand sufficient conditions, and as far as I know, this is sort of the first work that looks into, the semantic characterization and also the syntactic characterization of typability of ARA.
Okay.
Yeah, but if you want to know more about ARAs, then yeah, we can talk about it later offline.
Okay, great. So we're going to have time at the gather space after the session as well, right? So we can talk a little bit more.
Mm-hmm.
Great. Is there any other question from the audience? Do you like to comment a little bit more, anything about the work long?
Let's see. Not at the moment. Yeah.
Okay.
I mean, we're going to have plenty of time later at Gather, so maybe.
Sure,
yeah.
but because we have 4 minutes to wait, so.
Oh, okay, yeah.
So we can have a pause as well, but only to ask you if you have something else to talk about your project in general, or morally a little bit more about the big picture or this kind of things. It's okay.
Oh, okay. Yeah. I mean, I can talk more about ARA. So let's see. So usually when it comes to ARA, one popular question that people usually ask is that we use LB solving to do type inference, although we can deal with polynomial bounds in ARA. So there's a mismatch, right? Because when it comes to when people hear polynomials or multivariate polynomials, they are distinct from linear functions. And yet, when it comes to type inference in ARA, we only need to consider linear constraints, as in, LP, as in linear programming. So there's a mismatch, but well, it's fairly simple to see why we have this mismatch, because in ARA, we just infer the coefficients of polynomials. So when we want to infer coefficients, we only need to consider linear constraints, which is why we only need LP solving to do fully automatic type inference for ARA.
Really nice.
Yeah.
Okay. I really enjoyed your talk and slides, and I'm going to thank you again for the talk. Really inspiring.
Thanks so much. Thanks.
So now we're going to have 2 minutes break, and maybe, I don't know if Claudia could start sharing the slides, but we're going to start on time. Okay, so
yes. So the screen and the volume is okay?
Yeah, everything is fine. It's
Thank
really
you.
Fantastic. just 1 minute and then we start. In the meanwhile, let me just make another propaganda of the gather space we're going to have afterwards. So we are all invited to come and talk to the speakers. They are going to be there. It's a nice space for chatting and meeting people. So don't miss it. So, okay, so let's start the next talk. It's a real pleasure to introduce you Claudia Faggian, and she's going to talk about Factorization. It's a very nice title.
Thank you, Elena, and thank you to the organizer. So I'm presenting work in collaboration with Beniamino Accattoli and Giulio Guerrieri, and we introduce a new technique for proving in a modular way factorization theorems for compound systems such those that are obtained when extending call by name or call by value lambda calculi with extra features. Factorization is a co-standardization and is the base for analyzing reduction strategies and to define operational semantics. So let's put this in perspective. Lambda calculus is the paradigm that underlies high-order functional programming. And this paradigm has been enriched with more and more advanced feature, control state, non-determinism, probabilistic choice. And the well-established way to do so is to endow the calculus with the new operators and rules. And then you have to prove that the new calculus has a good operational properties. Clearly, the more complex and advanced feature we study, the more crucial become the ability to modularize the analysis. And in fact, this investigation was really triggered by concrete needs. So in my own case, this was the study of probabilistic lambda calculi with Simona Ronchi della Rocca, because probabilistic structure add complexity and indeed make the study of strategies painful. So we were searching the literature for tools to make such analysis more manageable and could not find. Indeed, a technique for a modular approach to termination and confluence are well developed. But when one focus on how to compute, then there is a very limited work and only few abstract technique. So factorization is the most basic property about how to compute. The paradigm is a head factorization. You have a sequence of beta steps and you can reorganize on first the head steps and then everything else. And this is a built-in block in proof of normalization and of standardization. But this can be abstracted. This holds for any computation and which has an essential reduction. The best way to put that is as Paul-André Méliès has done, the meaning of factorization is that the essential part of a computation can always be separated by its junk. So if you abstract from the role of head steps and you have a calculus which where you can separate, you can express some steps that are essential to the computation, some that are not. Factorization says that every rewriting sequence can be reorganized, can be factorized in essential steps, followed by the non-essential one. And in call by name lambda calculus, essential steps might be head steps, leftmost, outermost steps. In call by value, they are usually weak steps, but the principle is general. Very much like confluence, which is another fundamental key result, factorization is a non-trivial property to prove for lambda calculi, because beta reduction, which encapsulates the higher order of the calculus, requires sophisticated techniques like finite development, parallel reduction, and the difficulty compounds when extending the lambda calculus with the new constructs. And still, the difficulty usually originates by beta itself rather than the extra features, which is weird because we already know that beta factorize. And this is very clear when you look at the simplest modular technique for confluence, which is based on Hindley-Rosen lemma. You have two relations which are confluent, and their union is confluent if they commute with each other. It's a very basic result, but it's a powerful tool because what you gain is that you treat the confluence of beta as a black box. You rely on it, and you don't need to prove it again. And this makes a success in the literature of lambda calculus from Barendrecht book, where it's used to prove the confluence of beta eta, to a large number of advanced calculi from linear algebraic lambda calculus and many other, including our work on probabilistic lambda calculus. So in this paper, in this work, what with Beniamino and Giulio we developed is a technique for proving factorization in a modular way, which is very much inspired on Hindley-Rosen technique. So the idea is you have two factorizing relations and have condition, and you can state condition for saying their union is also factorizing. And follow Hindley-Rosen technique is quite natural, but doesn't appear to be ever used in the literature, at least of lambda calculus. And one reason is probably that a direct transposition of the technique does not work when extending lambda calculus because it does not interact well with beta. So the subtlety is that the lemma reduces the confluence of the compound system to just prove their commutation. The modules, the two components are already confluent, and you need to prove a condition that is commutation. But commutation is as difficult to prove as confluence. It's a global condition. It's a condition that is universally quantified on all sequence starting from an element. There is no gain here. The gain is that the commutation can be expressed in terms of local conditions. So in one step, you just need to check a simple diagram starting from one element. And this is what turned the lemma into a usable technique. And virtually all the work we know using Hindley-Rosen lemma in the literature, they prove commutation via Hindley strong commutation, which is the local variant. One step is a test, it's something you can effectively check. And this is what does not work, because if you just do a transposition, in principle, you can transpose Hindley-Rosen to factorization, is even folklore, but you again have a general global condition. And if you want to use the equivalent of strong commutation, it simply does not work, because essentially beta not only multiplies everything else, the added rules, but create steps that were not there. You start from something that is a non-head step and a head step, and in the postponement you create head steps. So the details are not important. The crucial point is that we need to find suitable conditions, because the natural transposition simply is not possible. And this is the contribution, the heart of our work. And the main result is that if you have two relations that have factorization with respect to some essential notion of step, their union also factorize if two local linear swap hold, where the pink steps, the essential steps, are linear, and the non-essential, the internal step, is postponed. When you apply this to extensions of lambda calculus, call by name or call by value, so you enrich with extra rules, this technique, this already simple technique, reduces it to an elementary test. So let me just start with pointing the terminology. So in lambda calculus, you have terms, and terms can include constants. So our calculus is not pure because we wanted to add the operator. We want an applied calculus. A reduction step is the contextual closure of a root relation, of a base relation, such as beta rule, or any other rule that you can associate, for example, to another constant. An extension of the calculus will extend either beta or its call by value variant with extra rules, or reduction for other constructs. So when let's see what happened with head factorization. The test become extremely simple. So we already have a beta reduction, and we assume there is another reduction, which is the contextual closure of some rule. The union satisfies head factorization if the rule gamma factorize, and then we only need to check one simple linear swap, which is the swap only with respect to the rule, to the root. The other swap always hold as long as the rule is substitutive. So you only need to check that beta non-head step postpone after the root rule, and the other is for free as long as the rule is substitutive, always hold. So let's apply. If we give several examples in the paper, I just like to show the use on non-deterministic lambda calculus, because it's really strikingly simple. Non-deterministic lambda calculus extend call by name lambda calculus, so beta reduction, with another rule which is non-deterministically choosing either P or Q in the redex. It's non-trivial because it's not confluent. The non-deterministic choice create beta redex, and the beta reduction duplicated choices, but still the Liguori and Piperno, which define the calculus, have shown that head factorization holds. And they prove the results via standardization following Klopp's technique. If you use, now we show, in fact, you only need to show a very simple lemma, that is this two linear swap with respect to the root reduction, so simply the base rule. And then you want to apply the test. Head reduction for the non-deterministic choice is simply given, is given directly from the first property. The root linear swap with respect to non-head beta steps is directly the second properties, and substitutivity is just given by the definition. So you only prove this simple lemma, and the result is automatically proved by the technique. And the same holds for several all the more common factorization schemes we checked. So in the case of call by value, you don't have head reduction, you have weak reduction. You don't reduce under lambda. And you can do that in unspecified order, what I write here, W, or in left to right order. And you have a similar test. You just you take the fact that beta reduction for call by value has weak factorization, and you only need to check very simple linear local elementary swap with respect to the base rule. The core of the technique, in fact, is independent from the specific syntax. It's become extremely simple when you work with lambda calculus, but the core technique, the condition to factorize a relation which satisfy the linear swap, their union factorizes, that holds independently from the structure. So also in calculus, where the objects are much richer. So the last example I want to give is the one of probabilistic lambda calculus. And there is a recent direction for calculi, which is you not only have a single abstract machine, but they are conservative extension of call by value, call by name lambda calculus. And one such calculus is the one that we introduced with Simona. And in the calculus, we prove confluence and factorization, that we call their standardization, but there is a deep asymmetry between the two results. Confluence is proved very neatly via Hindley-Rosen, and factorization is laborious. You need to define a parallel reduction of the extended calculus, and then we adapt Takashi technique. And the similar lot of work is in Leventis probabilistic calculus. You prove a head factorization for the probabilistic calculus via final developments, but the proof is equally laborious. So let me I just sketch the calculus, you don't need to enter in the details. The calculus, so this is the our call by value probabilistic lambda calculus. The objects that are rewritten are not terms, but are monadic structure, which are essentially distribution on terms. So a multi-set of terms with a probability. And the intended behavior of now the choice is that m plus n reduces to m or n with a probability. In this case, we have half-half. You have rules, you can give one-step rules for beta, you have the rules for the probabilistic choice, and the probabilistic choice, so the beta is unrestricted, is the contextual closure, the reduction is the contextual closure of the beta rule. For the effects, we restrict to weak context in order to have good properties like confluence. And then once you have this term-to-term reduction, you lift everything in the usual way, in the natural way. And this is the object you really do rewriting on. The calculus is distribution on terms and these lifted reductions. And in the paper, we show that factorization, each reduction can be factorized in weak step followed by non-weak steps. New proof. You only need one ingredient. That is, again, same as in the case of the non-deterministic calculus, is a simple one-step swap. the non-weak beta step commutes with the probabilistic step. And then you have all, because you have everything, because we use the technique. So weak factorization of beta, you have, because you here inherit from call by value Plotkin calculus. The linear swap of non-essential beta with the probabilistic reduction is simply this lemma that is 2 lines. And the other 2 conditions hold this vacuously because the probabilistic choice is closed, is restricted to weak context. The technique extends, applies also to any algebraic effect, whatever is commutative or non-commutative. This we have shown with Francesco Gavazzo, very recent work. So, summing up, you want to do an extension, you want to extend, you want to enrich your call by name or call by value lambda calculus. What you can do is to take beta or beta v as a black box. You add some extra constructs. The only thing you need to do is to check that the extra construct behave well, but normally the factorization is very easy because you don't have higher order. Higher order is where all the problem focus. And the only thing the user need to check is that the component interacts well. And in fact, the test is just elementary local commutations. And this is independent on the technique you used for proving the factorization of the components. And that's how I like to finish this talk.
Thank you very much, Claudia. Fantastic talk. So now we are open for questions. So please either, okay, so Simona already have a question. Please, Simona, you can.
Sorry. Can you hear me?
Yes, yes.
Yes. Thank you, Claudia, for your very, very nice talk. I have a small question. How robust is your general approach in order to be applied to more subtle notion of properties, for example, strong standardization, where a distinction between essential and non-essential reduction is not enough. We need to put at least 3 kinds of, or more than 3 kinds of reduction in order to have strong standardization. Can your procedure be iterated in such a way to grasp also the strong standardization, for example?
What do you mean by strong standardization? For example, what you do with Giulio Guerrieri in the refinement of call by value. Yes, we actually in the paper we also we have that exactly as example. Okay. Because, but in the sense that you actually can proceed in 2 steps. You have the factorization, and then in reality, what you do is some internal swap that are all local commutation. But for example, call by value and the sigma rules is our other main example, because we wanted to have something that is non-orthogonal, something non-confluent, something non-terminating.
So the idea is that you can use this also in case you want to order the inessential reduction, for example. This is the idea of strong normalization. To put an order between inessential reduction. Okay, thank you very much.
Thank you, Simona. And I think we should stop now. As I said at the beginning, we're going to have this gather space where we can all talk afterwards with Claudia a little bit more.
Okay,
so let's
thank you.
Thank Claudia again for the wonderful talk. Fantastic. So, okay, so let's move on the session. So maybe Haruka can put the slides on. So.
Okay.
Yeah, just let's wait for 1 minute more so we can start.
Oh.
No, now we can start. So let's move over let's go to the third talk of the session. So Haruka Tomita is going to talk about realizability without symmetry. Go ahead.
Thank you for the introduction. Today, I'm going to talk about constructing non-symmetric categorical structure by categorical realizability. Here is the outline of my presentation. I start with a brief introduction, then introduce the categorical structure we want to construct, then explain how to get the category, and finally summarize the result and the future work. Okay, I'd like to begin with a brief introduction. To begin with, what we call categorical realizability here. In semantics, it's common to give models of programming languages or logics as categories. The categorical realizability we call here is one method of giving a specific model. A simple structure called an applicative structure induces a category ASMA called an assembly on A. Properties of ASMA follows from properties of A, and consequently, we can prove the properties of these programming languages from these properties of applicative structures. A well-known application of this technique is strongly normalizing proof of system F using an applicative structure with the strongly normalizing property. Now let's take a closer look at applicative structures and categories of assemblies. Roughly speaking, an applicative structure expresses an abstract machine, and ASMA expresses a computable universe. The definition of applicative structure is very simple. A pair of a set and a partial binary operation on this set. For example, a monoid is an applicative structure by taking the product as a binary operation. And beta equivalence classes of untyped closed lambda terms also forms an applicative structure. From an applicative structure A, we construct a category ASMA. An object is a pair of a set and a function assigning each element small x to a non-empty subset of A. We call the elements of this non-empty subset as realizers of small x. A map is a function with a condition. The condition is that there exists an element R such that any terms obtained by applying R to the realizer of small x is in the realizer of fx. The result of the application of f and x is calculated by their realizers. That's why we call the category ASMA as an a-computable universe. As an aside, SMA ASMA has a full subcategory called modest sets on A. And the category of modest sets are more often used for models than the categories of assemblies. However, in our paper, we only deal with categories of assemblies, since all propositions introduced here also hold when we replace the word ASMA with the word modest sets on A. Anyway, now we get a category ASMA from an applicative structure A. In this presentation, I will focus on deconstructing from applicative structures to the categories of assemblies. Given certain conditions for an applicative structure, giving certain conditions for an applicative structure A causes corresponding properties of ASMA. Here are two well-known correspondences. First, let's look at definitions of PCAs and BCI algebras on the applicative structure side. A PCA is an applicative structure containing two special elements, S and K, such that satisfying these conditions. S is for substitution operator, and K is for discarding the second argument. Similarly, BCI algebras is an applicative structure containing three special elements, B, C, and I, satisfying these three conditions. B is for composition, C is for exchanging arguments, and I is for identities. An example of PCA is the untyped lambda calculus, and the example of BCI algebra is the untyped linear lambda calculus. And when an applicative structure A is a PCA or a BCI algebra, the categories of assemblies on A has a corresponding properties. That is, ASMA is a Cartesian closed category, or ASMA is a symmetric monoidal closed category. To prove these propositions, it is sufficient that components can be given proper realizers. For instance, in order to prove that the category ASMA of assemblies on the untyped lambda calculus has a binary product, we give realizers for pair elements and for projections. Here we nail the condition that the applicative structure has certain elements such as K. Now, these two correspondences are well known. However, there is no known classes of applicative structure that gives various categorical structures between SMCC and just the ordinary category. Our study is about giving new correspondences. When applicative structures are in these left classes, the categories of assemblies have these like structures. Especially for two of these, we also show better correspondences that properties of categories of assemblies induces the properties of applicative structures. And today I will introduce the BII cross-break algebra and the closed categories. Let's start with a brief introduction of closed categories. Closed categories are something like monoidal closed categories without tensor products. Its components are a locally small category C, an internal Hom functor bracket, a unit object I, and three natural transformations. In a monoidal closed category, we obtain the internal Hom functor as the right adjoint of the tensor product. On the other hand, In a closed category, we directly define the internal home functor and the relevant component. These three natural transformations are required to satisfy these 5 axioms. All of these axioms can be understood intuitively as internal home or function spaces. For instance, the first one states that the maps are invariant by compositing identity. So we want to get a class of applicative structures such that the categories of assembly is a closed category, but not ISMCC. But this is a delicate issue. Focusing on BCI algebras, the C is for exchanging argument, that is for symmetry. So can we make a closed category from a DI algebra without C? The answer is no, because there are realizers not generally for maps sent by the internal home functor. Forming a non-symmetric closed category requires something like a swapping operation. And this operation is what is done by C in BCI algebras and SMCCs. So in order to obtain non-symmetric closed categories, we need some weaker swapping operation than C. To solve this problem, we will introduce the following bullet operation. The bullet is a unary operation in an applicative structure such that x bullet y is equal to yx. We call BI bullet algebra as a BI algebra containing x bullet for each x. Like PCAs and BCI algebras, the BI bullet algebra corresponds to a certain class of lambda calculus. It is the planar lambda calculus. And here is the constructing rules for ordinary lambda calculus. In contrast to the ordinary lambda calculus, the linear lambda calculus eliminates 2 of the term constructing rules. While the planar lambda calculus furthermore eliminates the exchange rule. The planar lambda calculus is a BI bullet algebra. Moreover, the planar lambda calculus have a good correspondence to the BI bullet algebra. Like PCAs for the lambda calculus and BCI algebras for the linear lambda calculus, BI bullet algebra has a property called combinatory completeness for the planar lambda calculus. Roughly speaking, any closed planar term can be made from B and I using the application and the bullet operation. Please refer to our paper for the precise proposition of the combinatory completeness. Besides the planar lambda calculus, we gave these applicative structures for examples of BI bullet algebra in our paper. The computational lambda calculus is a BI bullet algebra and not a PCA nor a BCI algebra, since terms with computational effects cannot be swapped nor discarded. These examples also show that the BI bullet algebra as a class of applicative structure is indeed different from the BCI algebra. Back to realizability. Listed here are the components of closed categories. When an applicative structure A is a BI algebra, ASMA does not have several components because there are realizers not generally for these maps. On the other hand, when A is a BI bullet algebra, we can get most of the components. As for the rest, for the realizer of I inverse, we need to prepare another special element, I cross, such that for all x, I cross x, I is equal to x. We call BI I cross Brett algebra as a BI Brett algebra with I cross. In the planar lambda calculus, the B term also satisfies the axiom of I cross, and thus the planar lambda calculus is BI cross Brett algebra. To be more precise, the planar lambda calculus contains I cross depending on whether the signature contains constants or not, and depending on whether the eta equality is in the equational axiom or not. The important thing is that there is an example that is BI Brett algebra and not a BI cross Brett algebra, and there is an example that is a BI cross Brett algebras and not a BCI algebra. So therefore, BI Brett algebras, BI cross Brett algebras, and BCI algebras are different ones. From BI cross Brett algebras, we finally got non-symmetric closed categories. Moreover, something like the inverse of the proposition holds. That is, if ASMA happens to be a closed category and satisfies these 5 conditions, we can show that A is a BI cross Brett algebra. These 5 conditions are intuitively natural ones. For instance, the third one states that the natural transformation L is for the composition. The results of our study show that for other several classes of applicative structures, we can show that these classes induces the corresponding categorical structures. Especially for 2 of these, we can also show the inverse proposition. That is, assuming that ASMA happens to be a closed merge category and satisfies several conditions, we can show that the applicative structure is a BI Brett algebra. Also, we gave some examples and show these classes as certainly different ones from PCA nor BCI algebras. Finally, I'd like to talk about future work. The first thing to do is to find the correspondences other than the previous table. For instance, we haven't yet found the applicative structures inducing non-symmetric monoidal categories. There are also delicate issues. Take a BI cross Brett algebra A and assume that ASMA is a monoidal closed category. If we choose the realizers of tensor product as we do for BCI algebras, then ASMA inevitably becomes symmetric. Second, we want to find interesting examples of our new classes of applicative structures. Third, we would like to construct realizability models of exchange modality. It is known that we can construct models of exponential modality on the linear logic by categorical realizability using BCI algebras and some extra components, which are called linear combinatory algebra. It may be possible the similar construction for the exchange modality on the planar linear logic. That is all for my presentation. Thank you for listening.
Thank you very much. Very nice presentation. So we have a question. Yeah, go ahead. Alex?
Yeah, sorry, I thought Andre got a question in first, but yeah, so thank you for the very nice talk. I'm curious about the problem with the monoidal, with constructing the monoidal structure. So I wonder, is it possible to give a kind of polymorphic definition of a tensor product instead of the direct pair-like definition you're trying to give? So I think in polymorphic linear lambda calculus, you can define a tensor using a sort of polymorphic formula that works if you have sufficient parametricity. And I wonder if that's a way of trying to obtain a tensor product in the realizability categories you're in. Have you thought about that?
Is a question about constructing the models of polymorphic linear lambda calculus?
Well,
Or-
trying to find a tensor product that's a left adjoint to the closed structure that you have.
Let me see.
So somehow what you're addressing at the monoidal structure that you're talking about on the last slide here.
Last slide?
The very last slide. Well, anyway, at the end of the talk, you talked about difficulties in constructing a monoidal structure, and I'm wondering if one way of overcoming such difficulties would be to try to give an impredicative polymorphic definition of the monoidal structure.
Polymorphic definitions of monoidal structure.
Anyway, maybe it's something to think about. We can take it to Speaker's Corner because it's probably a bit complicated to discuss it now. So
I'm sorry.
I just wondered if you'd thought about that. So there are some other questions. So I think I'll
but it's a very interesting question actually. So there's another question by Giulio.
Yeah, thank you. Sorry, very naive question. Could you go back to the definition of ASMA?
Okay.
Yeah, sorry. It was at the beginning of your talk. Yeah, yes. That one. So the point is that in the definition of the arrows, so the maps in your category, I don't understand very well what is R. I mean, it means that there is an R for every function, there is an R, or this R is fixed once and for all.
So sorry.
You see the realizer R.
The realizer.
Yeah, I don't understand if is something fixed once and for all, or it depends on f on the function f, or the function, I mean the.
So, sorry, how can I say? You were asking about the
Okay, so I saw the answer. Okay, I saw an answer from the one organizer. He explained that. So
I'm sorry.
A morphism, F is a morphism if there exists an R that works for all X and A. Okay. Okay, so it's perfect. Thank you. Thank you to the CSL organizer who answered. Perfect. Thank you very much.
Thank you, Giulio. So is there any other questions? Well, if not, I would like to thank you again for the very nice talk. And we can continue the discussion later. It's going to be a nice discussion, I think. So, so maybe Willem can start also sharing the screen so we can prepare for the next talk.
So is that okay? Sound and
fantastic. We're just going to wait for 1 more minute to start, so we can start on time. It's great, yeah. Okay, so it's a pleasure to introduce Willem, and he's going to talk about a deep quantitative type system.
Thank you very much. This is joint work also with Giulio Guerrieri and Joe Paulus. Yes, there we go. So this is about looking at quantitative types in deep inference. And I've been working with the open deduction system. So what you see is derivations constructed from top to bottom. So I should say, I'm first going to tell you what the system is, and then I can tell you what we're going to do with it. It's because it's good to see this first, to have an intuition of what it looks like and why it's good to look at stuff in this system. So we're constructing derivations from atoms A, or from horizontal construction with a connective. So the star in the second constructor is any binary connective, or any, it can be unary, can be nullary, can be anything, and it can be contravariant in arguments. So some of these derivations can be upside down. And there is rule composition. So you put two derivations together with a rule that matches the conclusion of the first with the premise of the second. And then you can derive ordinary composition, the expected notion of composition, because when you plug them together, eventually you will hit a rule and it all works out. And you can capture intrinsic logic in this system quite neatly. So here are the derivations. So you've got an atom, top as a unit to the conjunction. The conjunction is as expected. Implication has a contravariant argument on the left, and rule composition is as just standard, not parametric in anything. And then you add the chosen rules. So we have abstraction, which is the eta rule, application, which looks as normal, and an n-ary contraction here. And we can use an n-ary version because we're using equality rules for the monodal structure of the conjunction. So what is nice about this? Well, let's first do an example of what this means in a Curry-Howard setting. So here we've got a red X at the top. Note also the size difference between the different constructions. On the left, we have the natural deduction, and on the right, we have the open deduction derivations for them. And I'll build these up inductively so that you can see what's going on. So we start with natural deduction, which has an explicit premise A and conclusion B. And here in open deduction, we can see a bit more about the structure of that derivation. We've got explicit formulas for every occurrence of X. And the first thing we need to do is contract those, add a contraction rule. And then in both sides, we can apply the abstraction. In natural deduction, this is a construction that is very familiar and very well known, but I consider it ad hoc in that it's external to the tree structure. It's a variable binding operation. It's specifically designed for the purpose. Whereas in open deduction, the whole structure is just following the general rules of how to build derivations. So you compose first with an implication, add the formula A on the left of an implication, and then you put the abstraction rule on top. And the application is in a way similar. In natural deduction, you build a tree structure, which is fine. In open deduction, you can see just a bit more that the argument and the function are joined by a conjunction. So what is the point of this then? When you look at proof systems and computational systems in open deduction, you get more structure. Everything is explicit and nothing should be ad hoc. And the hope is that from that we can get principled approaches to structuring computation. And that's what I've been doing, and others as well. So this work, looking at intersection types, quantitative types in this setting, is part of a larger project or a larger area that we are working in. And the idea is simply what is going on when we look at deep inference and what is the computational side of that. And we have a lot of different ways to do the duplication, mainly. That is the key thing we're seeing, and we want to interpret all of them. So here, the standard way to do a duplication is to have a contraction with a premise above it, and then you duplicate the derivation above it. And that gives you categorical combinators, but it's also related to explicit substitution, the standard way of duplication. What we've seen in a different way of duplicating, you can take your contractions and make them atomic, which means when they are not applied to an atomic formula, you introduce a medial rule, which you can see at the bottom of the result construction, and then you get two smaller contractions, and one is a co-contraction upside down. And this method of reduction gave the atomic lambda calculus, and current work is trying to answer the question how this relates to sharing graphs, because it looks an awful lot like it. And there's another way. This goes together with the first method of duplication, because it's not really a method of duplication, it's a method of propagation. So normally when you have an abstraction, it's stuck at a radix. You cannot execute the duplication separately from the beta radix. And in open deduction, you can see, like literally see in front of you that it can be moved through. And the question is, if you do that, what do you get? What is the computational side of that? And in a linear logic setting, it relates to sharing graphs, but it's not quite the same thing. And here in this work, we're connecting this to intersection types and resource calculus. So the aims of the whole project are to use deep inference to give a principled, robust, structural, uniform account. I can add more adjectives if anyone has a need for them, of typed lambda calculi more widely, and intersection types and resource lambda calculi specifically in this work. So let's look at what intersection types really are. I'm using my own ad hoc rules, so forgive me if they are unfamiliar. But the basic idea is that instead of contracting the premises of a derivation when you do an abstraction, so if you have a number of occurrences of X of various types, normally you'd ask them to be the same type, and you collect all of them and you just give that type as the antecedent of the implication. Here you make a collection instead. You make a collection of those types with various algebraic properties. And then when you have an application on the right, you want to, so that's if the function expects a collection of certain types, then you have to provide an argument of each type, which has to be the same term at that type. And the nice thing about this is that it characterizes strong normalization by typability, so if and only if. resource lambda calculus is very related, except you're not making collections of types, but collections of terms. So the application is explicitly to a collection of arguments, and the abstraction is explicitly over a collection of variables. And other than that, everything is linear, so variables occur linearly. And then you can characterize strong normalization by an expansion operation. If you have a lambda term and it expands to a resource lambda term, then it is strongly normalizing. And it's an if and only if. Now, what does the transformation in open deduction that we're looking at, what does that have to do with all this? Well, let's look at it. So here is a radix and a type derivation for it. And we're going to look at the blue contraction rule. And it's going to do the permutation through the proof that I promised. First, it's going to go across through the abstraction. And then it's going to go down across through the application rule. And in the process, it expands the type of the rules that it traverses. And then it's in a position where it can actually duplicate the argument to the function in the standard way. So what happens is if we permute contraction through a radix and, or through applications and abstractions, we are carrying out the expansion from a lambda term to a resource lambda term. That is what we're seeing here. And that's the key insight and the basis of this work. So the result of that transformation is an intersection types resource lambda calculi. So the rest is just formalizing that idea, really. I'm putting here the rules for the intersection type system next to the constructions we saw in the previous slide. So the result of that transformation, and it just matches perfectly. Except there's one thing, there is no distinction yet in this system between the conjunction and the intersection type operator. So that is a problem because we know, or it has been looked at, and intersection types are not conjunctions. That is known. So the simplest solution is to make this a separate operator. And we've used a plus for that because we're thinking of these as collections. So we're thinking of plus as combining collections. Starting to formalize this type system, we're defining basic types as atoms and implications from collections, and these are types for terms. We've got collection types, which are just abstractly generated from an empty collection and injection into it, and a singleton, and a sum operation on collections, and those will be the types of variables. And then we need types for the context of a derivation, so the premise. And those are conjunctions over collections. So those are the formulas, and in open deduction, the formulas, the connectives immediately give the structure of the derivations. All you need further are the rules. So let's look at the rules that we need. The operation we want to have is to combine two derivations together in a collection type, in a collection with our sum operator. And the problem then is that the premise is not of the right shape. That is a sum of conjunctions, and it should be a conjunction of collections instead. So it's a collection of conjunctions, and it's the wrong way around. The rule we have to add to make it work is a medial. And this is really very interesting. There are a lot of interesting things and interesting results that happen in deep inference because of the structure of the derivations, and quite a few of them rely on medial rules to work. So this is a very typical rule for deep inference, and it's responsible for a lot of the results we have seen. So that it pops up here too is both a good sign and just very interesting. It means we are really using the power of the proof system to do something interesting. Well, I think it's interesting. The next thing that we need to change is if we have if you have a self-application XX, which should be typable, then the application rule puts them in a conjunction. But when we combine them into one, the type for a variable should be a collection. So what we need is we need to adapt the contraction rule to change the conjunction into a collection. And I'm reading the rules bottom to top there. So those are the two rules we need. And note that we have not said anything about the nature of our collections. We've said, so the only thing I've said is that what the constructors are and what the rules are for interacting with the conjunction. Those are the only things that we've specified. Other than that, what algebraic rules you want to add to this is up to you. We've taken associativity, unitality, and symmetry in the system so that it at least looks like and walks like and quacks like a lambda calculus, but you might as well drop those, not a real problem. And then to get various flavors of intersection types, normally you add idempotence or not, that's the main distinction, but we can work with inequalities as well. We can do, and those are actually better behaved. So we can use redundancy, which covers deletion, and duplicability, which covers duplicability. And then we add a rule to the type system to implement that. So you can, this is a kind of a forgetful rule. It's not a semantic rule. So this is the rule that makes this symmetry non-deterministic. So reduction with this rule is non-deterministic because it forgets about the underlying connection between the connectors at the bottom and the top, or the atoms at the bottom and the top. And it covers all the structural rules of the calculus. And here's how you would reduce with that. It simply commutes with the constructors and the derivations that you add, that you may use those constructors with. And bottom right is then, here is how it implements duplication. So this is the proof system. It's not giving me this, the rules shouldn't be here yet, but anyway. So the derivations are as before, but now we add the unit for the collections and the sum. These are the rules we had before, minus the contraction rule, because we've changed that. Here is the n-ary contraction rule, and the n by m medial rule, and the inequality rule for the algebraic collections. And the medial rule is quite versatile. So at the bottom, first is the unary version of the contraction, and then the nullary version. And then the medial has 4 variants listed. So 0 by 0, 0 by 2, 2 by 0, and 2 by 2. And those are all, sort of, you have to squint a bit to see what it means. Not all of this stays very intuitive working with it, but it all works out. And to go with this, we have a calculus as expected. It's a resource calculus. So we have variables. Application is to a collection, has a collection as argument. Abstraction and sharing, it's an explicit substitution calculus, and the explicit substitution also has collections as argument, and collections are generated by empty and singleton and append. This is the type system. So a variable has an atomic, has any formula. Application is as before. Abstraction is as before. You add a contraction, except now the formula for the variable is a collection of all the formulas in the conjunction. And the explicit substitution is basically a red X, and produced red X. It's a contraction that's in the middle of a derivation. So this is how the type system captures explicit substitution quite naturally. If you have a contraction rule that is not directly attached to an abstraction, it is an explicit substitution. And then we add the construction for collections, which works as follows. So you take the derivations for the terms in the collection. At the bottom, you can add an inequality. And at the top, to close it off, you need this construction, which matches up the variables. So if you have different variables in each of the gammas, then you need to weaken them in the others, and that looks like that. I'm short on time, so I'm not going to explain all that. And then reduction uses the same laws as you have for the types. And here are the rules, and I'll quickly go over those. Beta reduction is at a distance. The calculus naturally has at a distance reduction, so that means the red X is not blocked by a sequence of explicit substitutions. In the second line, the duplication happens if you have an explicit substitution with a variable that occurs at least twice, then you duplicate it. And the inequality stems from the fact that you can apply, so before evaluating an explicit substitution, you apply the inequality rule, so the reduction for the algebra of the collection. So the use of these algebraic laws is not to consider terms modulo them. They are part of the reduction relation, and they are affected whenever you would do a duplication or a deletion in dealing with an explicit substitution. So, for instance, if you in the third rule, which evaluates a singleton, if you have a larger collection but you have redundancy, then you can reduce your collection to a singleton and then reduce, so that it selects one term from your collection. And finally, there's a deletion rule. And a list of the results we have for this calculus, which is what I'm ending on. So we have confluence modulo the non-determinism of the symmetry of the algebra. Strong normalization when typed. You can add or remove algebraic laws to give bounds on reduction paths that are exact bounds, lower bounds, or upper bounds. You can switch between resource calculus and intersection types by demanding uniformity of the terms in your collection. So if they all represent the same term, then you have an intersection type system, and otherwise it's a resource calculus. You can add a strength law to differentiate between strong normalization and weak normalization in an intersection type system. And we're still, well, we did some work trying to encode existing systems into this, but we haven't done all of them, suffice to say. Thank you.
Thank you, Willem. Very nice talk. So Delia has a question. So Delia, go ahead. We have 1 minute for questions. Oh, okay. So you can. So Delia doesn't have a microphone, so you can type, and I can read. Okay. Yep.
Okay, that's fine. Thank you. That's fine now. Thanks, Willem, for your talk. So I have a question. You probably know already my question. My question is the following. I mean, non-idempotent types are able to give quantitative information about reduction, and you get quantitative information about the calculus, which is more or less inspired from linear logic here, not really inspired from deep inference. So the calculus that is inspired from the inference is your atomic lambda calculus. And the question is why it was not possible to give a non-idempotent intersection type system for the atomic lambda calculus, which is the one corresponding to your intuitionistic deep inference logic.
Well, not possible is well, we don't know yet. There was enough work in this to stop right there and think about that another time. No, there is, yeah. Doing intersection types for the atomic lambda calculus is quite hard, and what we're doing with that is trying to find the right formalization of the rules so that the intersection types become natural, and that's been left off somewhere in the middle. And the problem is that that the atomic calculus characterizes full laziness, but it does so in a way where weakening is very hard to deal with.
But the problem with weakening appears in almost every calculi with XP substitutions, not only in the atomic lambda calculus. So weakening is not a precise problem of the atomic lambda calculus. It's a more general concept. But node replication, what I call node replication, which is the model of substitution that you have in the atomic lambda calculus, this is particularly, I mean, this is something which is inherent to the atomic lambda calculus, and this is the difficult part, I think, the difficult issue. But I don't know. I thought that I mean, from this work, we can have somehow a hint about what would be needed to interpret node replication with a quantitative theory.
Willem, I'll have to interrupt you. I'm so sorry because we are over the time. So Delia, you can maybe join this gather space so we can talk a little bit more about this.
Sure.
No, thank you so much. Thank you, Willem, and thank you all for being in the session. It was a really nice one. I enjoyed myself a lot. So now I invite you all to come to the gather space, and then we're going to have invited talk and then the closing of CSL. So I would like to thank you all for attending CSL. And thanks again to Willem. So see you all soon. Goodbye.